Are you able to see the screen?
Yes.
The presentation? Okay, great, great. Thank you so much. Thank you so much, Jose, for the lead-in to a continued discussion regarding recent research projects, and to my team for the opportunity to share highlights of these projects. These recent projects have been conducted, of course, on the LH Post facility, and I would echo Jose's sentiment that our colleagues, both at UCSD and other users, have a wide range of experience, and I've benefited personally from very fruitful discussions to help advance a variety of research agendas. And I thought perhaps in a very short time here I could just share some recent contributions in the understanding, in particular, of the building system associated with use of cold form steel framed systems. Oops, there we go. So in particular, I thought I would focus on two projects. They're coined the CFS HUD project and the CFS NERI project. They have a little bit of a storyline that goes on together. The CFS NERI project is a large collaboration amongst 3 universities and industry, and is an ongoing activity that will culminate in the years to come using LH Post 6. Now we will benefit as well from using the newly upgraded facility following the CLT program. We're slated to perform these tests in 2022. My hopeful outcome in 12 minutes is to demonstrate the success of industry academic collaborations through this example. So in each of these little sub-projects, I tried to highlight our colleagues in industry that have given tireless hours to contributions of a variety of academic researchers. This first activity, coined CFS HUD, was really focused on earthquake and post-earthquake fire performance, in this case of mid-rise cold form steel framed buildings. And the hopeful outcome was really to develop an experimental basis for future design of mid-rise CFS buildings. So central to that effort was a design and testing of a 6-story cold form steel building. It had a layout representative of multifamily residential occupancy, so that was the scope. Uniquely, it was a panelized construction. In fact, the entire test building was erected on our shake table in about 9 days. A mass of panelized shear walls and panelized floors designed to present code provisions. The anticipated performance was really one of load-resisting elements which would develop tension zone yielding within steel sheathed shear walls erected and arrayed throughout the structure. And so you can see some of those components here, the repetitively framed subsystem wall elements, a continuous tie rod assembly that spanned from floor to floor, prefabricated, relatively stiff floor diaphragm assembly. We performed a wide variety of tests on this specimen, beginning with low amplitude white noise. And in fact, we did everything we could to it, including tapping the building with tires, as you can see in this diagram here, this photograph in the upper right. We performed base earthquake tests, 3 active earthquake test days with a day in between for physical inspection, and those kinds of features. Thinking about that aspect in the protocol was important for us in terms of understanding and allowing us to document the state of the structure, analyze the data, and prepare for the next day. We conducted 2 floors of live fire tests. It was the second time we had experience undertaking live fire tests on a real physical structure on our outdoor facility. I think it went pretty smoothly. We obtained some interesting results. I won't share any of those in our short time here, but it's something to think about. The post-earthquake fire behavior of a system is certainly uncharted territory in our community. We then performed an aftershock and what I would say maybe an extreme earthquake test, trying to understand the post-thermal earthquake response of the structure. So I do have a couple of results. There are very, just a few, just to highlight some things one might think about during the measurement process. An overarching, benefit of performing full-scale either component or system level tests on the shake table is our ability to understand what the evolution and dynamic properties is of any system or component. It's something we can readily determine using the shake table. So here's a family of plots articulating the shift in period with increasing severity of earthquake motion or increasing state of damage of the structure, both the period and the damping ratio extracted from before and after white noise tests. And so, you can automatically pick out some, in addition to understanding the initial state and when and how it's preserved through the intensity of shaking, you can also understand when there's abrupt shifts in period, such as your design target event, associating that with physical damage, like in this case, fortunately, the design yielding tension zone mechanism was readily visible on several floors of the structure. And then subsequently at design, and uniquely for this structure, before and after the live thermal test, very little shift in the period as the system had already readily softened and settled into its state of behavior. So these kinds of features were really important, understanding sort of the learnings of what a building may undergo. It's also very useful, of course, to calibrating high fidelity computer models. Lots of other valuable data coming from these types of tests. Peak inter-story drift ratio, something you might want to look at right away. The family of data here are broken into so-called service level scaled motions, low intensity. You see their inter-story drift, floor-to-floor drift is less than about 0.2%. The physical damage also was evident of this sort of immediately readily available functionality of the structure. As soon as you get into above service level design events and well above design events, this last and final motion developing very large interstory drifts at the lower story of the building. One interesting feature, if you sort of look at the family of plots from the left to the right, you see the belly, let's say, of the demand shift to the lowest most levels of the building structure. You see very large interstory drift actually at the second floor level of the structure. Those were right after the live fire experiments were performed on this structure. I'll try with some bravery to present some videos. I think I have to stop the, there we go. Hope you can see this. This shows you what are some interior views of the second floor of this building. My son playing piano in the background to enjoy before cookie time. Okay, so these are some of the views of the interior of the structure. These are short little subclips, and you can see the shear wall framing next to gravity wall elements. The shaking is happening left to right in this isometric view taken from a GoPro camera. And you can see the very dramatic tearing and abrupt tearing under this near fault pulse, this final near fault pulse, the tearing of the sheet steel, both along the vertical and horizontal edge. You can see just a hint of the tie rod assembly providing the redundancy and framing action. So we can learn quite a bit from these types of interior views. Here's another view of another room. We'll stop it after this one. This is also a little interesting to look at. This is the transverse wall where my cursor is here. My cursor is right here. This is the longitudinal wall, which you can see the rapid development of the plastic yielding due to the buckling, and then the abrupt tearing. You can see daylight through the edge there. So it's a very useful understanding of the interior view of this structure. The final picture of the building is very telling, and I should mention in this slide that one can collect information regarding, of course, the residual state of the structure, and you can see that second level of the building developed a full plastic mechanism. We were really inspired, I should say, before we began this program by Professor Restrepo's use of GPS sensors, and these types of global views of a large structure help emulate the importance of thinking outside of the box when capturing large permanent displacements. For example, we wouldn't have been able to have that opportunity without a distribution of GPS sensors spanned up the elevation of this structure. And there's some views from the inside. Another view of the full development of a plastic hinge at that second level. So what did we, to continue the story, that one can learn with large physical tests like this, what did we not learn and what questions remained? And I think, many of us in research move along these lines. We have a little bit of slow inertia as we're going, but we didn't think about the importance of exterior finishes on the structure. we didn't have a sense of the genericism of structural shear walls, particularly in a system level where loads need to span from floor to floor. We simply laid them out as they might have been in a multi-residential unit. We didn't take careful look at the diaphragm, for example, and its flexibility. You know, with a single test like this, we didn't have the opportunity to consider other diaphragm arrangements. We also, in the concert of CFS framed systems, we didn't look at the importance of what someone might refer to as non-designated load-bearing systems. And here's a good example of that. During the erection, you can see the shear wall system on the left and the gravity assembly and openings for doors and the like on the right. They by nature, the architect requires us to lay these out in line, yet we don't really know what their contribution is. So at least for us as researchers, the story continued, and we teamed up with Johns Hopkins and University of Massachusetts Amherst and a number of other additional industry partners. And we've begun a second project coined the CFS NEARI project. This is just one little snippet of some work we did on the shake table. There are various facets of this project and various partners involved with the project. But we have just a limited time to take a look at how we backtracked a little bit, went back and looked at what an archetype building might be, and there had been some work done by Shahab Torabini and Ben Schaefer on characterizing more readily utilized layouts of typical buildings, validating them and defining them as archetype buildings. We tried to help expand this thought process to very tall CFS frame buildings. So you see a simple layout here. This is actually going to guide us in our 2020 test program, actually, the work that was done as a part of that effort. And then to get ourselves started in understanding this issue of non-designated systems, I think one good contribution we made here was testing what we called inline wall specimens. These are components. You can see the components up here on the right. We did some complementary work in our laboratory. This is just to give you a picture of what you can do sort of not only out on a shake table, but perhaps cross comparison to quasi-static tests. And we looked at a whole bunch of issues that we felt were lacking in the literature, not only in the CFS HUD, but elsewhere. That was the effective finishes, exterior finishes, openings, they're readily distributed throughout architectural layouts, different detailing features, like what's referred to in the codified world as type 1 versus type 2 walls. That's simply tie rods at the end of a wall versus extending and tracking the load path and preserving or minimizing the tie-down assembly. Types of tie-down assemblies, tie rods, hold-downs, symmetry in the layout, and the like. And our whole goal here was to really look at the lateral load sharing between shear walls when they're placed in line with gravity walls. So I don't have time to go through the test assembly, and I know we're all not at the shake table, and we all want to be there. So just to share with you, some useful tools I think we have at the facility. We have a couple of drones available to us as researchers, and this is a drone view taken of the assembly, so I could use it sort of in twofold. You can see these are simple pairs of walls holding a seismic mass. We tried to use the real estate of the shake table by putting two of them side by side, and benefiting from the fact that they would be simultaneously loaded under similar motions. I have a couple of slides on, just some select results from these experiments. This is a useful video to look at to articulate the kinds of things that we're able to glean from these component level shake table tests. I want to credit my colleague, Professor Cara Peterman, for affectionately referring to her first impression of these now earthquake excited walls as a so-called happy dancing steel walls, because this type of feature isn't seen, this type of elastic buckling, isn't readily visible when we go into the laboratory and we take a look at emulating the dynamic load with quasi-static or pseudo-static loading. So very good information can be gleaned when we actually are able to complement quasi-static loading with shake table testing. And we're also able to track through, for example, from the elastic to the quasi-elastic to the design. And then in some of our cases, we're able to restrain the top of the specimen and monotonically pool and exaggerate the demand upon the specimen. And so you see a family of knowledge gained in terms of the force displacement hysteretic response. This is for a symmetric shear wall, gravity, shear wall baseline specimen, what we defined as we defined it as our baseline or simplest, most idealized specimen. This work continued with a variety of variables. I'm pretty much out of time, so I'll show this and then just go to the very end. This is a useful way to perhaps look at one of the results. You can see the happy dancing steel elastic buckling that's ongoing, and then all of a sudden a very abrupt drop in the global force displacement and correspondingly in the tie rod assembly forces due to the near full tearing along the length of the edge of the sheet steel, the extreme edge of the sheet steel. And this belays and modifies the damage mechanism that one observes when you have a symmetric layout. So those are important learnings, I would say, from these isolated component type tests. Okay, in the interest of time, I'll go to my last slide. I tried to, I know we have a number of colleagues who were able to join us today, and both from academics and from industry. And we particularly appreciate our industry colleagues joining us for this workshop. At least my experience, as an academic researcher, I may sometimes come up with some wild ideas. My industry colleagues can sometimes help pull me back to the realities of construction practice, and that can make our work together, so much more valuable for obvious reasons. So I really feel in the spirit of this workshop that our industry collaborations, for those of us that are in academics, are really essential, particularly in these large scale testing endeavors. So I think, as a final remark, I think industry academic research teams, hold the promise to make real change in understanding and improving the performance of both structural and non-structural systems during earthquake events.